In this lesson, we're going to cover Chebyshev's theorem and the empirical rule. Now, these two rules make a statement about the percent of data that lie within so many standard deviations of the mean for any data set. So first of all, let's take a look at Chebyshev's theorem. Chebyshev's theorem makes a statement about any data set. So if you're given any set of observations, either from a sample or a population, then the proportion of values that lie within k standard deviations of the mean is going to be at least 1 minus 1 over k squared, where k is any constant greater than 1. Now this is maybe a little bit confusing, so let's take a look at a graphic illustrating what's going on here and what this is stating. So here we have graphed the distribution of some values from an arbitrary data set. You can think of this as perhaps being like a histogram right here. Now we have our mean right about here. That's the mean for the data set. That's about where these values would balance out. Okay. And right here we've moved off 2 standard deviations to the right and 2 standard deviations to the left. Okay, so for this data set, mu is our, keep in mind, mu is our mean, and sigma, that's our standard deviation, and we would have to calculate those numbers, or those would have to be given to us. So once again here we've moved 2 standard deviations to the right and 2 standard deviations to the left, and this number would be mu minus 2 sigma, mu plus 2 sigma. Now if you look at the k value in this case, the number 2 is your k value. And if you calculate 1 minus 1 over 2 squared, you get 0.75. So Chebyshev's theorem says at least 75% of all your data is going to be between these two numbers. At least 75% of all your data is between those two numbers. It could be more than 75%. And if your distribution is nice and bell-shaped or normally distributed, then it will be much more than 75%, as we'll see, and that's what the empirical rule discusses. Now, notice here also that if we were to move away 3 standard deviations to the right and to the left of our mean, so right here is mu plus 3 sigma, and here is mu minus 3 sigma. So here we've moved away 3 standard deviations to the left and right. Then if we evaluate down here 1 minus 1 over k squared, keep in mind here now the k is 3 now. And if we evaluate 1 minus 1 over 3 squared, that's 8/9, and that's about 0.89. So Chebyshev's theorem says between these two numbers, you have at least 89% of all of your data values are between these two numbers. And once again, it could be more than 89% if your distribution is normally distributed or bell-shaped. It will be more than 89%. So let's take a look at an example using Chebyshev's theorem. So here's an example. So the arithmetic mean biweekly amount contributed by the Dupree paint employees to the company's profit-sharing plan is $51.54, and the standard deviation is $7.51. So our question then is, at least what percent of the contributions lie between $25.26 and $77.83? So what we have to do here is we're given that the mean is 51.54, and right here would be about 77.83, and let's say down here is 25.26. Now what we have to do is we have to calculate how many standard deviations is this number and this number away from 51.54. So we want to know how many standard deviations is that distance. So to do that, we simply evaluate 77.83 minus 51.54, and we divide that by the standard deviation that we're given for the data set, 7.51. And if you do that on your calculator, you can check it out. You will get 3.5. So this distance right here is 3.5 standard deviations, or the total distance here is 3.5 times 7.51. So it's 3.5 standard deviations. Now to apply Chebyshev's theorem, this quantity right here, the 25.26, would also have to be 3.5 standard deviations away from 51.54, or else we couldn't apply Chebyshev's theorem. And that is the case. If you check out 25.26 minus 51.54, and you divide that by 7.51, you will see that you do get negative 3.5. You do get negative 3.5. So this distance is also 3.5 standard deviations from the mean. So then Chebyshev's theorem makes a statement. If we evaluate 1 minus 1 over 3.5 squared, as we have down here, you will get approximately 9.92. And so Chebyshev's theorem says at least 92% of all the contributions made to this profit-sharing plan were between 25.26 and 77.83. And so that's an example of how we apply Chebyshev's theorem. And keep in mind, the key thing here is the wording at least 92%. It could be more. Chebyshev's theorem gives you a lower bound on the percent of data within so many standard deviations of the mean. Now let's take a look at the empirical rule. So the empirical rule makes this statement. For a symmetrical, bell-shaped frequency distribution, you can think of a normally distributed set of data, approximately 68% of all the observations lie within one standard deviation of the mean. So in other words, if you look at these two numbers, mu minus sigma to mu plus sigma, between these two numbers you will have approximately 68% of all your data lying between those two numbers. Now, we also have that 95% of all the observations will lie within two standard deviations of the mean. So if you look at these two numbers, mu minus 2 sigma to mu plus 2 sigma, about 95% of all your data will be between these two numbers. And then finally, if you look within 3 standard deviations of the mean, you will have virtually all of your data, or 99.7% of all your data, will lie within 3 standard deviations of the mean. So if you look at these two numbers, mu minus 3 sigma to mu plus 3 sigma, 99.7%, about 99.7% of all your data will lie between these two numbers or virtually all of your data. Now it's important to note that the empirical rule only applies to normally distributed data or nice bell-shaped data. It's also important to note that these numbers 68, 95, 99.7 are only approximations. The amount of data lying between, let's say within 2 standard deviations is approximately 95%. It could be a little less or it could be a little more for any particular data set. Now down here we have a little graphic illustrating this. So for this data set that we have graphed down here, the green curve, we have that the mean is 100 and the standard deviation is 10 in this case. So if you move away 1 standard deviation from the mean, so if you go between 90 and 110, about 68% of all your data will be between those two numbers. If you move away 2 standard deviations, so you go from 80 to 120, then about 95% of all your data will be between 80 and 120. And finally, if you move away 3 standard deviations from the mean, or you go from 70 to 130, then about 99.7% of all your data will be between those two numbers, or virtually your entire data set will be between 70 and 130. So that's a graphical illustration of the empirical rule. Let's take a look at an example. So here we're given that the height of women have a bell-shaped distribution with a mean of 63.6 and a standard deviation of 2.5. So for this problem, we're assuming mu is 63.6 and sigma is 2.5. What can we conclude from the empirical rule about the percentage of women that have heights between 58.6 and 68.6? So we have to evaluate how many standard deviations are these two numbers from 63.6. So let's look at 68.6 first. If we evaluate and we divide that by 2.5, notice that we get 5. The numerator is 5 over 2.5, and that is 2. So this number is 2 standard deviations from the mean. Now to apply the empirical rule, we would also need that 58.6 be 2 standard deviations away from the mean as well, or else we couldn't apply the empirical rule. So we need to check that out. So if we look at 58.6 and we divide that by 2.5, we will get negative 5 over 2.5, and that is negative 2. So yes, 58.6 is also 2 standard deviations to the left of the mean. And therefore, by the empirical rule, since these two numbers are 2 standard deviations away from the mean, and we're assuming that we have a bell-shaped distribution, or a normally distributed set of data, then we can conclude that approximately 95%, we'll say it like that, approximately 95% of all women have heights between 58.6 and 68.6 inches. And that concludes our discussion about Chebyshev's theorem and the empirical rule.